Hello, Dr. Nat here. Welcome back. We're doing chapter 15. We're still in chapter 15 and this is the fourth part. Thermal processes in gas. Okay, so here I have the syringe that we have seen multiple times now. And you're gonna say, boringnya kena belajar pasal syringe lagi. Kau sabar jap, nanti kena belajar benda lain. Ni sikit lagi. Okay, so previously we talked about how Abu moved the piston by a certain distance x. And the work done by Abu was F because he is pushing the piston, so he is using force over a distance x. So work done by Abu is W equals to F delta x. And the same amount of energy is absorbed by the gas system, which means that if Abu is losing energy, that energy goes to the gas system. Okay, so we have this equation W equals to F delta x, but how do we make this more relatable to a gas system? So if you guys can recall from chapter 13, we learned about pressure, and pressure is equal to F over A. Okay, so I'm going to try to substitute this guy over here. Okay, so F is equal to PA. Okay, so I just rearrange. I put A over here on the other side. So W is equal to PA delta X, and delta X is just a distance, right? So let's just say this is X. So area times X, what does that give you? Area times X gives me delta V times P. So work done is equal to P delta V. If we were to relate work done to a gas system. So again, area times a distance or area times a height is equal to delta V. So work done can be described as pressure times volume. Does that sound more relatable to a gas system? Yes. So work done on the gas system is equal to P times delta V. Okay, so now let's talk about what happens when delta V is positive and when delta V is negative. So when delta V is positive, we are expecting that the V new must be greater than the V initial, right? Because V new minus V naught or V initial would be greater than 0. So that is a positive. And a negative delta V is when V new is much less than V initial, or V new minus V naught, and the answer is less than 0. So that would give us a negative change in volume. So this is a positive change in volume. This is a negative change in volume. Positive change in volume maksudnya volume dia membesar lah. Okay, so dia makin besar. Whereas negative change in volume, the change in volume makin kecil. Okay, so smaller volume lah in the end. Okay, so if I were to push this piston, what happens to my volume? My volume becomes smaller. W equals to P minus delta V. So this would give me a negative work. But I just told you, if the environment is doing work, this is Abu, right? The Abu over here. So Abu was pushing and Abu was losing energy, and the energy should have gone to the gas system. And I told you, if Abu is losing energy, gas system gets the energy and W should be positive. But in this case, if I were to look at this equation, I would see that the final volume is this much, right? The V new is much smaller. Is smaller than the V initial. What was our V initial? We started with this amount of volume. This is our V naught, and we ended up with V new. So V new is smaller than V naught. If V new is smaller than V naught, then we would get negative change in volume. Okay, so this would give me a negative work done, which is not the case because we already discussed that our gas system is supposed to get positive energy. So how should I rectify this? So for me to rectify this equation, this equation should be W equals to minus P delta V, which means that if the change in volume becomes smaller, which means that the environment is doing work on the gas system, so the volume becomes smaller, the work done on the the work done on the gas system is a positive W when volume is smaller. Okay, so this equation is not W equals to P delta V, even though we tried to convert it from W equals to F delta X, but for a gas system, the equation should be W equals to minus, let me use a different color for that, minus P delta V. And this is in your module book, I already written this. Your W for your gas system, the work done is equal to minus P delta V. Okay? So let's do a little recap. Abu is losing energy. Abu is the environment. Abu is losing energy, which means that the gas system is taking energy. So Abu rasa penat by 10 joules. He loses this much of energy which goes to the system. So W equals to 10 joules. This energy is positive, so let's see if our equation works now. So negative P delta V, let's say the pressure is let's arbitrarily select a number, so let's say it's just 1 atm. And then our delta V, our V new is smaller than our V initial because Abu is pushing the piston. The volume inside the syringe becomes smaller, so negative change in volume. So this is a negative change in volume. Previously the volume was, let's say, 100. After Abu pushed it, it became what? It became like 90 centimeter cube. So 90 minus 100 is a negative 10. Negative 10 is negative V lah. Okay, so this is negative times negative, you get a positive work done. So yes, our equation works now. So the one that we talked about just now where we assumed the pressure to be constant is called isobaric. And there are 3 more other thermal processes in gas, which is adiabatic, isovolumetric, and isothermal. So isobaric means, I already told you, it's constant pressure. Okay, so this guy is constant pressure. And what does adiabatic mean? Adiabatic means your heat energy is equal to 0, which means that no heat energy is released or no heat energy is absorbed by the gas system. And number 3, isovolumetric, you have the word volume here, so it means V is constant. So V is constant here. And isothermal, okay, in isothermal, the temperature does not change. Okay, so we talked about isobaric, isovolumetric, isothermal. What on earth is iso? Iso means same. Same pressure, isovolumetric. So same volume, isothermal. Can you guess? Isothermal, same temperature, or T is constant. Now, where is T in our equation? We have the equation, which is the first law of thermodynamics. Let me copy that really quick. If we were to talk about constant pressure, we know that our W has a constant P. And if we are talking about adiabatic, we know that our Q is supposed to be 0, which means that if this guy is 0, then delta U is equal to W, because Q is 0 plus 0, so you can just not write it. So delta U is equal to work done. And for isovolumetric, you know that the volume is constant, so this guy, the V, becomes constant. And then for isothermal, the T is constant. Now where is the T located? We can't see it. I don't see it in this equation. Do you see it? Okay, so T for this equation comes from the internal energy. Remember, U equals to 3 over 2 nRT. So if T does not change, it means that your internal energy cannot change, because internal energy is equal to 3 over 2 nRT. These guys, for sure, you can't change it. R is a constant and N is the number of moles. The only thing that you can change here is T. So if T is constant, your U is constant, which means that U final minus U initial would be 0, because these guys are equal. So U final does not change from U initial. If I started with 10, I end up with 10. 10 minus 10 is 0. So what happens? My internal energy does not change. If my internal energy does not change, my delta U is equal to 0. So delta U equals to W plus Q. This guy becomes a 0. So what happens to this equation? It will become Q equals to minus W. Okay, so the heat energy absorbed is equal to the work done by the gas system. That is why it's a negative W. Negative W means positive V of the gas. Positive V of the gas. Okay. So the gas expands, which means that it is doing work on the environment while it is absorbing, while at the same time it is absorbing heat. Okay. For an isovolumetric process, the V is constant, which means that when V final minus V initial equals to a 0, the work done is also a 0. So work done for an isovolumetric process, the work done is equal to 0, and this means that your delta U is equal to Q. And so we will talk more on these 4 thermal processes in gases. Hopefully you guys will understand better.